Okay, my goal in this video is going to be to derive this equation P sub I, or P initial V initial to the gamma equals P final V final to the gamma, where gamma equals C sub P over C sub V. Now all our textbook said about it was it can be shown that PV to the gamma is a constant. Now it might be worthwhile to read this rest of the chapter and see if it is shown somewhere else in the chapter. However, I'm extremely impatient and I want to know right now. So I looked up adiabatic process in Wikipedia and found they have there the same formula, PV equals constant, or rather PV to the gamma equals constant. And specifically gamma is C sub P divided by C sub V, which is the degrees of freedom plus 2 divided by the degrees of freedom. So for an ideal gas, gamma is 5/3, and for a monatomic ideal gas, gamma is 5/3, and for a diatomic gas, gamma is 7/5. And they add to that the caveat that this is only applicable to classical ideal gases and not Bose-Einstein or Fermi gases. What's the difference between an ideal gas, a Bose-Einstein gas, and a Fermi gas? Well, that's probably the topic for later. Now, here is the word that I was looking for, derivation. Let's hope that this will lead to somewhere down here. What do we have? P over P sub naught equals V over V sub naught to the power of negative alpha plus 1 over alpha. That looks fairly promising, since apparently alpha plus 1 over alpha is the same as gamma. They call that formula here the continuous formula for adiabatic heating and cooling. Let's begin. The definition of an adiabatic process is that the heat transfer to the system is 0. Now, our notation is that the heat transfer is Q. I think their notation may be that the heat transfer is delta Q. Well, let's make a note. Their first equation is du plus delta W equals delta Q. Our equation was delta U plus the work done on the environment is Q. Now, what's the difference? Well, for one thing, this D represents a total derivative, while this delta represents only a partial derivative. And I am kind of speculating here because I'm kind of guessing what the person that wrote the article meant. My trouble is, without knowing exactly what variables they are using to define U and W, it is difficult to be sure what they mean. And in any case, I think it would be wrong to put a partial derivative here, because if work is equal to the integral of pressure dV, on second thought, maybe it is a partial derivative, because I'm thinking along the lines of some kind of ultimate quantity. Let's imagine a quantity that we're going to call PV. And imagine taking a partial derivative of this thing, or imagine taking the total derivative of this thing. Then you would get P dV plus V dP. However, V dP has nothing to do with the work, because if the volume is not changing, there's no work being done. So you would want to take a partial derivative of PV with respect to the volume, and then you would get P. So let's put this out like this. PV equals PdV, which is probably what they mean by the delta W. I guess the name for that symbol is del rather than delta. On the other hand, the U variable is a mixture of the potential energy of the like the chemical potential energy of and latent heat energy of the particles plus the thermal kinetic energy of the particles. And I'm not sure exactly what variables to use that you would take a derivative of to find out what that broke down to. Okay, after all of that speculation about what they meant by del W, I find that pressure volume work is defined by, I can't get that to highlight, del W equals P dV, which is basically what we have right there. Why the confusion? Well, because strictly speaking, the work is not equal to the pressure times the volume of the gas. Strictly speaking, the work is equal to the integral of the pressure times dV. Strictly speaking, the derivative of the product PV is PdV plus VdP. Now, if you integrate that, you don't get the work. On the other hand, if you take the partial derivative of PV with respect to V, you just get P. And now, if you integrate that with respect to dV, then you do get the work. So we'll just take a partial derivative of this line here, del W, and take a partial derivative of that, which means what? We're just removing the integral sign? I'm not sure if that's strictly mathematically legal or not, but that's what they did. Del W is equal by definition to P dV. Now let's look at equation 3 and compare it. This equation about the internal energy of the gas is the same as what we've been using, Nc sub V delta T. Actually, we've talked about it as delta U equals Nc sub V delta T, where you recall that for a monatomic gas, C sub V was equal to 3 halves R, and for diatomic gas, C sub V was equal to 5 halves R. So basically this alpha is that number there, the 3 halves or the 5 halves. So it's kind of interesting. This this is a differential kind of thing, while this is a absolute kind of thing. Basically, the assumption here is that there is no internal energy in any other form except for thermal kinetic energy. I've also put in my notes, I'm not sure if it's gotten into the videos yet, that I'm going to make this statement that the specific heat, the internal energy specific heat, is the same as the isovolumetric specific heat. If you have a certain number of particles at a certain temperature in a small box, and the same number of particles at the same temperature in a large box, it doesn't matter how big the box is, they both have the same amount of internal energy. It's a function only of the number of particles and the temperature. That's probably why they use a total derivative here, because we're only concerned about the change with respect to the temperature, the change in internal energy with respect to the temperature. We don't care about, well, we take it for granted that the number of particles is not going to change. If the number of particles changed, of course, it would be du equals c sub v times n dt plus dt dn, which is the use of the chain rule. But since we're assuming that the number of particles does not change, it will just be du equals n c sub v dt, or n alpha r dt, where alpha is that property that they introduce. In any case, let's see if we can use equation 3 and the ideal gas law to derive this equation here. If we have u equals alpha n RT, then du equals alpha n r dt. If we have PV equals nRT, then dPV equals dNRT. Well, it would be nR dt. Then I'll just multiply this by alpha on both sides and see what I get, so that this matches this, and then we can make the claim that du is equal to alpha d of PV, derivative of PV, which is equal to alpha n r dt. Then we go ahead and do the derivative of this, which uses the chain rule. Du equals alpha times p dv plus v dp. This p dv is identifiable as that del work that we had earlier. So we're going to have du equals alpha times del work plus v dp. So we have this extra term in here, the VDP, that we haven't really identified yet. We can also combine that, or use the ideal gas law. I'm sorry, not the ideal gas law, the first law of thermodynamics, which says what Q is equal to, let's see, the heat added to the system is equal to the work done on the environment plus the internal energy of the gas, which in Wikipedia is written del Q equals del W plus du. And since this is an adiabatic reaction, this is going to be 0 because there's no heat going in or out of the gas. Just an exchange of internal kinetic energy of the gas into work, or vice versa. That means this thing simplifies to del W equals negative du. And we can take that and plug it in. Now I'm trying to remember what we're trying to end up with. Where we're trying to go is that PV to the gamma equals constant. And the question I'm wanting to know is, do we replace the U with a W, or do we replace the du with negative del W, or do we replace the del W with a negative du? Well, we want one that is a function of P and V. Du is a function of nRT, while del W is a function of P and V. So we want these. So we'll replace the du with a negative del W. So this will become negative del W equals alpha times del W plus V dP. And then add alpha to both sides, so it'll be, rather subtract alpha from both sides, it'll be negative alpha minus alpha plus 1 del W equals V dP. Then we want to make the replacement del W equals P dV, which I've said was a definition. So I'll have this negative alpha plus 1 del W, or P dV equals V dP. Now we want to separate the variables, which means get all the volumes on one side and get all of the pressures on the other side, and see what comes out. Negative alpha plus 1 times dV over V equals dP over P. Now it's time to integrate both sides. So I'll have negative alpha plus 1 times the natural log of volume equals the natural log of the pressure. And I better put an integration constant in there somewhere. Okay, I'm looking back at the Wikipedia article. It looks like I'm not quite on track with what they have. They have an alpha dP over P. I have just dP over P. Where did I go wrong? I went wrong right here in not distributing through this alpha to this VDP. There should be an alpha there, and an alpha there, and an alpha there, and an alpha there. The next thing the Wikipedia article has that I didn't do was it introduced the integration constants in the form of their final values, initial pressure and initial volume. So in essence, instead of a single integration constant, they have an integration constant on both sides, k sub v and k sub b, let's say. And with some skipped steps, they figured out that that integration constant has to come out equivalent to natural log of v over v sub naught equals alpha natural log of p over p sub naught. I divide both sides by alpha and kind of swap them around and get this, and then they take, let's move this over, and take e to the power of that and e to the power of that. E to the natural log of something is just p over p sub naught, and then let me try something. Or let me just remind you of this. A to the power of b times c is equal to a to the power of b to the power of c, or a to the power of c to the power of b. So in any case, this thing comes out to be equal to v over v sub naught to the power of negative alpha plus 1 over alpha. Now alpha equals c sub v over r. So this would be c sub v over r plus 1 divided by c sub v over r, which is the same thing as c sub v plus r over c sub v, which is c sub p over c sub v. So we can take this thing and change it to p over p sub naught equals v over v sub naught to the negative gamma. Let's divide this side by, or let's divide both sides by v to the negative gamma and p sub naught, and then divide or multiply both sides by p sub naught. So p sub naught over p sub naught cancels, and over here we'll have over v sub naught to the negative gamma. And then expressing that with positive exponents, we will have pv to the gamma equals p sub naught v sub naught to the gamma. And that is the equation that we were trying to derive. It took a long time. I think the key steps to this was taking the derivative of u, du, the derivative of pv, and then figuring out which part of that pv is actually doing work, which part of it is not, and getting it into this differential equation, which was an expression of the relationship of the change in pressure to the change in volume. Once we had that relationship between dp and dv, it was possible to establish a relationship between p and v.